we've already seen that enantiomers are stereoisomers that are non-superimposable mirror images of each other. There's another type of stereoisomer called a diastereomer, and diastereomers are stereoisomers that are non-superimposable non-mirror images of each other. And let's take a look at this example to see if we can figure out what a diastereomer is. So here I have a molecule that has two chirality centers. So there's one for the carbon that's attached to the OH, so that one right there is a chirality center. And then the carbon attached to the methyl group is also a chirality center. So this would be carbon 1 with the OH, and then the carbon attached to the methyl group here would be carbon 2. So when we talked about stereoisomers in an earlier video, the total number of stereoisomers is 2 to the n, where n is the number of chirality centers that you have in your molecule. So in this example, we have 2 chirality centers. So we would take 2 to the second power, which is obviously equal to 4. So for this dot structure, we could draw 4 stereoisomers. So 4 stereoisomers. Now, this number that you get is actually the maximum number. It's possible to have a smaller number than this, and we'll see an example of that in the next video. So I could draw 4 different molecules that have this same dot structure to it. So let's see if we can do that. So we'll start with our cyclohexane ring. And for this first stereoisomer, we're going to have the OH group coming out at us, and we're going to have the methyl group coming out at us. So that's one possible molecule. Second stereoisomer, we're going to have both of those groups going away from us. So the OH group is going away from us, and the methyl group is going away from us. And in my third stereoisomer, I'm going to have the OH coming out at me, and the methyl group going away from me in space. And for my last stereoisomer, I'll have the OH going away from me, and the methyl group coming up at me in space. So these are your 4 different combinations that are possible for that dot structure. And if you were to take the time to assign an absolute configuration to these chirality centers, for my first stereoisomer, you would find that you would find that for this carbon right here, it's actually R. So that's carbon 1. So this would be 1R. And then at carbon 2, it's actually S. So it'd be 1R and 2S. For the next stereoisomer, it would turn out to be 1S and 2R. For the next one, it would be 1R and 2R. And then for our last example, they would both be S. So you could go ahead and assign absolute configurations for practice. So if I'm trying to think about how to classify my 4 stereoisomers, I look at the first 2 examples, and I think to myself, how are my first 2 molecules related to each other? Well, let's go up here and refresh our memory about the definition for enantiomers. Enantiomers have opposite configurations at all chirality centers. So sometimes you could think about them as being mirror images. That works. Sometimes it's easier just to look at the structure and say, how do the configurations compare at all of my chirality centers? And you can see that at carbon 1, we started with a wedge over here on the left, and then we switched it to a dash over here on the right. And that switched our absolute configuration at carbon 1 from R to S. So at carbon 1, we have an opposite configuration at our chirality center. At carbon 2, over here on the left, we had a wedge, and then we switched it to a dash over here. So we went from S at carbon 2 to R at carbon 2. So we have absolute configurations at all chirality centers in this molecule. So these 2 molecules are mirror images of each other, non-superimposable mirror images, so they are enantiomers. So these 2 are enantiomers to each other. So enantiomers. When I look over here at the 2 on the right, I can see I have a wedge at carbon 1, and it turned out to be R. And over here I have a dash at carbon 1, and it's S. So we have an opposite absolute configuration at that chirality center. At carbon 2, I went from a dash, an R, to a wedge, and S. So once again, I have an opposite configuration at all chirality centers. So these two molecules would be examples of enantiomers. So they're mirror images of each other. All right, so what exactly is a diastereomer? Let's look at the definition. Diastereomers have opposite configurations at some chirality centers. So let's just change color here so we can identify some diastereomers. Opposite configurations at some chirality centers. So not all of them. So that's really the key when you're looking at stereoisomers. So if I were to compare, let's say, the first stereoisomer here with two wedges to, let's say, this one right here, which has one wedge and one dash, I do not have opposite configurations at all chirality centers. I only have an opposite configuration at the second chirality center, at this one, at carbon 2. So these two are diastereomers of each other. So in red are my diastereomers. And this is just one example, right? One example of a pair of diastereomers. You could very easily take this molecule over here, right, the one with two dashes, and then you could say that molecule is a diastereomer with this molecule, because this molecule over here on the left has two dashes, and the molecule over here on the right has one wedge and one dash. So they do not have opposite absolute configurations at all chirality centers. Therefore, they are diastereomers of each other. So if you take one of the first two molecules over here on the left and you pair it with one of the two molecules over here on the right, that would be a pair of diastereomers. So hopefully that helps clear up the difference between those different types of stereoisomers. Let's do a quick overview of isomers so we can compare all the ones that we've talked about so far in this course. So we'll do a quick little isomer overview here. So what are the different types of isomers that we've talked about? Well, in an earlier video, we talked about molecules that have the same molecular formula, but they differ in terms of their dot structures, and we call these structural isomers. So that's one type of possible isomer, a structural isomer, also called a constitutional isomer. So I'll go ahead and put that in parentheses here. So these have the same molecular formula, but they differ in terms of their structure. They have different dot structures. The atoms are connected in different ways. Well, the other type of isomer would be, of course, stereoisomers. So these are molecules that have the same dot structure, if you will, but they differ in 3 dimensions. So if we go back up here and we look at this dot structure that we drew right here, right, we were able to draw 4 different stereoisomers that had the same basic dot structure. Okay, so that's the idea of a stereoisomer. It has the same structure, but in terms of how those atoms are in 3 dimensions, you can generate different molecules. So same dot structure, but different 3-dimensional molecules. And there were 2 types of stereoisomers that we discussed: enantiomers. So we have enantiomers here, which we know are non-superimposable mirror images. And then we have diastereomers. So diastereomers, which we know are non-superimposable, non-mirror images of each other. And sometimes when you make enantiomers, your goal is to separate them. And one of the ways to do it would be to convert enantiomers into diastereomers. And since diastereomers have different physical properties, they're easier to resolve and separate, and then you can regenerate your enantiomer. So that's one way to separate enantiomers. So we've done an overview of isomers, and we've talked about the difference between enantiomers and diastereomers. In the next video, we'll talk about meso compounds.